So now that you've got a pretty comprehensive view of what's a stream, what's a sequential stream at least, what are its relevant pieces, what are the aggregate operations, intermediate operations, terminal operations, its overall structure and functionality. We talked about terminating a stream. We talked about splitting data sources up into chunks to be used by a stream and making a stream out of a data source. And then we talked about implementing custom collectors. Now that you know all that stuff, I'm going to show you a couple of examples to kind of make it all concrete. And these will hopefully be good guides for the programming assignments we'll be doing later. And the example we're going to look at is something called the SearchStreamGang program, which is a really cool program. And if you really want to know everything it is to know about cool uses of streams and other Java 8 technologies, take a look at this code. And what's particularly cool about it is that it's got a whole bunch of different implementations of the same functionality. So every one of these, there's about 10 different implementations here. Every one of these different implementations will do the same thing in a different way. And what's cool about that is not only to see that there's lots of different ways to do the same thing, but the really cool part is if you look carefully, you can see that some ways of doing these implementations are way faster than other ways of doing things. And of course, the reason for that is that the parallel versions will leverage the inherent hardware efficiencies on your machine, your multi-cores, for example, in order to run a heck of a lot faster. And that's what we'll see. We're going to start looking at something very simple, which is the sequential version. And I'll show you how it works. And you'll see it's not that fast. But the cool part is, which we'll talk about later, not today, but later in the course, in order to get it to run a lot faster, all you have to do is one simple sleight of hand, and you change the factory method .stream to .parallelstream, and boom, it all runs a lot faster. So that's that's kind of the foreshadowing of where we're headed with this stuff. So I'm going to show you how to write the sequential stream using the various techniques we're going to talk about to teach more about streams, and then we'll just speed it up with a flick of a wrist, and it goes way faster. The particular methods we're going to focus on are the process stream and process input methods. They're going to show off the different Java 8 features we want to focus on. And this program is a lot more interesting than the simple search stream program, especially when we start to jazz it up with parallel computing. So SearchStreamGang is a Java 8 revision of an earlier program I wrote, which you can also take a look at, that uses Java 7 features, or Java 7 and before features. In particular, it uses the Java executor framework to do a bunch of tasks in parallel by using the embarrassingly parallel nature of the problem. The problem is to search for a bunch of phrases in a large number of files. That's an embarrassingly parallel program, and so we can speed it up through parallel computing. I won't spend much time talking about these examples here. If you take the course in the spring, we'll cover this stuff in more detail because we'll talk about the executor framework. So SearchStreamGang gets rid of the older stuff that we did with simple search stream. Remember, we did this earlier. We did the do, re, mi stuff. And this is going to be much more interesting because it's going to look in multiple strings instead of one string. And it's going to be used to search for phrases rather than searching for individual words. So that'll add some additional cool stuff like regular expression matching that's more powerful. And it'll also demonstrate how to process things in parallel better. The way it works is it uses regular expressions to search for phrases in the works of Shakespeare. I'm a Shakespeare fan, but it's really an excuse because there's lots of Shakespeare text out there you can search. You can download the entire work of Shakespeare here. And I think he has something along the order of 37 plays and a whole pile of sonnets. So let's assume, for sake of argument, that we've got a bunch of works of Shakespeare. This is a little excerpt from Hamlet. And you want to look for a phrase, the classic phrase, brevity is the soul of wit. You want to find where that phrase occurs. And so this program will tell you that phrase occurs in this play at this offset from the beginning of the play. And in fact, what's the other thing that's cool about this, more from a technical point of view, is the fact that we can use some powerful regular expression techniques to actually search for phrases that span multiple lines. So if we want to look for a phrase that spans multiple lines, we can actually find that here. And I'll show you how to do that with a regular expression. And that uses some cool regular expression pattern matching features that are at least worth being aware of, even if you don't use them at the moment. The actual implementation of SearchStreamGang uses this framework, which has a whole bunch of different Java 8 concurrency and parallelism strategies. So it has parallel streams. It has this thing called a parallel splitterator, which is basically even more parallel than a parallel streams approach. It has completable futures. It's also got a bunch of other things like RxJava. So if you're familiar with RxJava, which is a reactive streams model, it's got a couple of different variants of that as well. What's cool about this is you can do the apples comparisons between all the different approaches. So they're all doing the same thing, but you can see that they have wildly different performance characteristics. So the ones that run sequentially, of course, are slow because they can't leverage the inherent parallelism on the platform. And then certain of the parallel versions run way, way, way faster. And we'll show them later. OK, so let's first see how this works with the sequential version. There's a particular class here, which you could find if you went to the release. And it's called search with sequential streams. And it's got two methods, process stream and process input. These are methods that I wrote, of course. And they demonstrate a bunch of streams features. In particular, as you'll see, they demonstrate the stream factory method, the map, collect, and the filter method, and show how all these aggregate operations actually get used. The process stream method uses a sequential stream, in other words, a stream running in the main thread, to search a list of input strings where each string corresponds to another work of Shakespeare, a different work of Shakespeare, in one thread of control. They all take place in one thread, and each input string is a different work of Shakespeare. So that's what the strings are. Process input is used to search for phrases in a given input string. So it also uses a sequential stream. It uses the same sort of control, actually, that the process stream method does. And it will search a given input string, a given work of Shakespeare, to locate all the occurrences of phrases in that work using one thread of control. So let's first visualize this, and then we should have some time to show the code. And that'll probably be it for the day. So process stream takes this list of input strings. So you're inputting a list of input strings, or it's obtaining a list of input strings from the file system. And it converts that list of strings into a sequential stream by using the stream factory method. So we go from a list, which is shown as the green. The green round angle is the list that has a bunch of input strings, so we convert that into a stream of strings. We then feed that stream of strings into the map operation. And what map operation is going to do, it's going to call the process input method. We'll talk more about what that does. I'll show it to you. And process input will then search for phrases in each input string. So process input takes a given input string and then searches for the phrases in that. And that creates a stream of lists of search results. So what we'll basically have is we'll end up with, for every work of Shakespeare, we'll have a list of search results that correspond to any place we found a match there. And what you can see is that this changes the type. So we had a stream of strings going in, and after coming out of the map aggregate operation, we have a stream of lists of search results. So it's a different type. It's kind of like, morphing, or like a caterpillar turns into a butterfly. It's transforming itself. And map can do that. That's one of the things that map can do. Then the final thing we do is we collect the lists of search results, and by calling collect, that will trigger the intermediate processing, which causes these other operations to run. And it will then create a list of the search results that come through this. So we have a list of search results based on so-called encounter order. An encounter order is just the original order that the works of Shakespeare were encountered, right? So if, Hamlet came before Macbeth, which came before Twelfth Night, that's the order in which the output will come through as well. Okay, so that's what process stream does. Process input, as you saw, was kind of this subroutine that's called in the process stream processing. And it takes a list of input phrases to find in a given input source, which in this case is an input string, a work of Shakespeare. And the stream method converts the list of search phrases into a stream of search phrases. That gets fed into the map method, which calls search for phrase. And search for phrase will take a look at each phrase, and it'll try to find it in each input string. So for every phrase, it'll go and see, is that in this work of Shakespeare or not? That returns a stream of search results, one search result for every phrase that's being looked up. And some of the things that we're looking up may actually be empty. So in that particular case, we're going to filter out the results by getting rid of anything that's empty. And that'll remove empty search results from the stream, and we'll end up with a stream of search results that only contain the ones that had something that was not empty, right? So only things that actually match will be included here. Then we go ahead and call collect, and as you know, collect triggers intermediate processing, and then it creates ourselves a list of search results, again, in encounter order, where encounter order in this context is the order in which we look for the search phrases themselves. Everything here runs within one thread of control. That's why it's kind of slow relative to the parallel versions. And we'll show later how we can parallelize all this stuff using parallel streams. And the magic thing to remember here is the only real change between the sequential version and the parallel version is the sequential version uses stream as the factory method, and the parallel version uses parallel stream. And that's really about it, right? So we're going to get this n-fold speed up, where n is the number of cores or hyperthreaded cores, and it'll speed things up tremendously by making one little teeny-weeny change in the source code, going from sequential to parallel. That's really cool, and that's the magic of the streams framework, is because it's all done in a functional way, and you don't know or care how it works under the hood, you can go from one model to another with almost no effort on your part, once you get the sequential version working, which is cool. So it only requires a real minuscule change to do this transformation. All right, now that we've talked about the visualization and I showed you what it looks like, let's take a look at the code. So the first thing we'll look at is the part that maps the input strings through the process stream method. Here's what process stream looks like. It calls a helper method in the framework called getInput, and that just gets a list of all the strings, where each string contains a work of Shakespeare. And the getInput method is something defined on a base class called StreamGang, which is then inherited by SearchStreamGang, and then we have specific implementations that figure out how to handle this input in a particular way. That's just good old-fashioned framework inheriting a reusable capability that's defined up the inheritance hierarchy. GetInput returns a list of character sequences. We use character sequence instead of string because strings substring method actually makes a copy. When you call substring on a string, it actually makes a copy of the data, which can be rather expensive. In contrast, subsequence on a sequence doesn't need to make a copy. It can simply return like a little header that points back to the same data. So that works in situations where you want to have a lot of read-only data and be able to point to different parts within the overall buffer of the data. So it's much more optimized in terms of space utilization and also copying overhead. So it's faster from a time and space point of view. You can read this link to find out more about the difference between subsequence and substring. So we use a list of character sequence for this reason. What this thing is going to return when we're all done is a list of lists of search results that correspond to everywhere where we found the matches in the elements in the input. And I'll show you later, and later probably is next time, next Monday, how to flatten this list of search results into a stream of search results by using the flat map method. So flat map, like a steamroller, flattens out structured data into a stream of sort of atomic or elementary data. And that makes certain things a lot easier. All right. A search results class is simply this class that's going to store the number of times a phrase appears in an input string. So given a particular input string, or for a particular work of Shakespeare like Hamlet or whatnot, and given a particular word or phrase like, brevity is the soul of wit or whatever, it will go ahead and store a list of all the times that phrase appeared in that work of Shakespeare. So that's what a search results object is. And this is kind of interesting later when we talk about converting stuff between how filter and map work. Here's the actual implementation. We take the input list, which is this list of all the works of Shakespeare. We convert it into a stream, and then we do the processing here. So this is a sequential stream pipeline. Stream is just a factor method. And if you recall, if you look at assignment number, if you look at the skeletons for assignment 1B, you'll see that there's stream and parallel stream. And if you look there, stream just uses stream support dot stream split iterator false. So it'll basically make a sequential stream out of the list. We then call the map aggregate operation, passing in the process input behavior. We'll look at process input in just a second. And what that's going to do is it's going to search everything in that input string, trying to find all the phrases. And process input returns a list of search results, one list for each input string. We collect those results together, triggering the intermediate processing, and make a list of lists of search results as the return value from this type, from this method. So that's the code. Very canonical, right? Almost every piece of code you'll write with streams converts some data source into a stream, does a bunch of processing with map or filter or whatnot, and collects the results into some type of container. So this is just kind of the canonical way of doing things. Here is process input. If you recall, process input is used to look for occurrences of phrases to find in a given string. And here's what the implementation resembles. You have process input. It takes a character sequence which contains a work of Shakespeare. It splits that character sequence up, and that should be input sequence, not input string. And it creates essentially a title and an input. So the title is like, Hamlet, Tragedy of Denmark, or Macbeth, or whatever. That's the title, and then the rest of it's the actual text for the play. We use subsequence to avoid overhead of copying strings. And then we say, for each phrase we're looking for, please turn that list of phrases into a stream of phrases. And then we're going to go ahead and apply a couple of intermediate operations. We're first going to search for the phrase in the input pile with this particular title. And the false flag here says, do this sequentially, don't do it in parallel. We'll change that later in a couple weeks when we talk about parallel streams. So this is a lambda function that looks for all the phrases in the input stream, and it returns an output stream of search results. And we'll talk about search for phrase later. The filter method here will go ahead and get rid of anything that's empty. So if it's empty, and we negate that, that means it's not empty. So we let things pass through the filter that are not empty. So we let not empty stuff or stuff that's got actual search results through the filter. Notice how this implementation uses a method reference and a negator predicate lambda. You could also write the code like this, which simply uses the lambda expression to say, is the result size greater than 0? That's just another way to do it. I kind of like this approach better. I'm a bit more of a fan of method references because I find them a little more concise, but this works too. These are intermediate operations. They are triggered when collect is called, and that converts a list result, which should have a list of non-empty results in it. That is stored here, and we return that as the result of the method. Okay, so that is the end of that example. And next time, we'll take a look at more interesting features like flat map and grouping by for how to actually print the results of this.